Welcome back to my third lecture on elliptic curve cryptography. So last time we were talking about Diffie-Hellman and El-Gamal and digital signatures, which are really nice algorithms for encryption. They're based on the discrete logarithm problem or the elliptic curve logarithm problem, the elliptic curve discrete logarithm problem. But as I said, these are very ingenious, simple ideas, ingenious ideas that might have ingenious attacks that we have not discovered yet. So I wanted to tell you at least one of these attacks. This is called the man-in-the-middle attack, which is a very serious concern nowadays for things like Diffie-Hellman, for a key exchange. So the problem is that Bob and Alice might be trying to communicate, but Eve might be in the middle. Well, it's not clear who is in the middle here, but Eve might be listening without them even realizing. Okay, so that is the problem here. So suppose we set up a Diffie-Hellman system. Here I'm setting up for Z modulo P cross. But it can be for any group. You have a Diffie-Hellman, you have a group with a point of high order, with an order that is very large or very much divisible by a very large prime at least. And then you do this type of algorithm. You pick a secret exponent, Bob picks secret exponent, then computes that G to the A, and Bob computes G to the B. And then they send, these are publicly available. A is sent through an insecure channel. B is sent through an insecure channel. But each one of them can retrieve their keys. The secret key, because they can compute B to the A and A to the B, and that is the same number key, K. Okay? So that is great, because now they have a key exchange, and they can start communicating using another method that is essentially also public. What method is going to be used for encryption, right? So how is this not secure? The problem is that Eve can set themselves in the middle, and you might never know that you are not talking to Bob. So here's how it works. Eve intercepts or embeds herself in the conversation by by cracking sort of like the connection. And then Alice publishes A and sends it through a public channel, presumably to Bob. But instead of going directly to Bob, Alice thinks she's communicating with Bob, but Alice is actually communicating with Eve. So Eve receives this message A, and we'll send the message forward, but not exactly the same message. Alice communicates with Bob in sense A, and Eve will send E, her own multiple of the point, and does the same thing with Bob. Sends a B and sends an B sends the B, and Eve sends the E forward. Then what happens is that now they have set up two different keys, one for Alice to talk to Eve and one for Eve to talk to Bob. So these K over here, now Alice can start sending messages, encrypts it, sends an encrypted message to Eve. Eve knows the key that Alice is using, so Eve can take that message, decode it, listen to it, encode it with the key that they've set up with Bob, and send the message forward to Bob. And all that Bob knows is that this message makes sense because it is the message that Alice sent to Bob. So Bob gets the same message that Alice sent, but Eve in the middle is listening. And backwards, the same thing happens. Bob can encrypt messages, start with a plain text, encrypt it. Eve can decrypt it and send it back to Alice. So there is no issue here. This is perfectly doable if you are in an insecure channel and somebody intercepts that you're going to start a communication and sets themselves in the middle. So this is a very big problem for this kind of key exchange. So what is the solution to something like this is to use authentication. The authentication starts from Alice would send, both Alice and Bob set their own authentication. So you know that that message is coming from Alice. So if at the same time also Alice sent this is the part A, if it had a signature, I don't know, like, like a copyright symbol or something that has been authenticated that is coming from Alice, then when Bob receives E instead, can check, is that actually coming from Alice? And Eve does not know how to make signatures like Alice does. So this would trigger some alarm that this is not the right key. This is not the right code that would come from Alice, because that's not Alice. And vice versa, Bob would have to also authenticate the key so that when Alice receives this message, Alice knows that that is not coming from Bob. Okay, so that is also what happens when we do, so as I said, for example, many encryption messages, encryption systems, they are using elliptic curve Diffie-Hellman, but on top you are first verifying that you are who you say you are, so that there is nobody in the middle listening to all the conversations. As far as we know. Again, this is an ingenious way to embed yourself in a conversation, but there might be, for all we know, other ways to also fake the signature, right? So there might be other ingenious ways of doing that. Okay, so great. So let's move on. In cryptography, what I wanted to talk about next is RSA. So we're going to move on. So we've seen the methods that are like the Diffie-Hellman, Elgamal, that are based on discrete logarithm problems. So let's talk a little bit about RSA. I'm going to tell you how RSA works and see that it's built on a different problem. So RSA, as I said, it was discovered in 1977. But in 1973, there was already some secret way of something that was equivalent to RSA. Anyway, it was published in 1977, and then they had a patent by 1983. Rivest, Shamir, and Edelman. And as you can tell, they decided not to name RSA alphabetical because it spells something else. Okay, so RSA is going to be based on essentially Euler's theorem. Remember that for Euler's, we have a way to know what is the order of an element, or what is a power that works, that a to this power, the Euler phi function, that is phi of n, is the Euler phi function. And that gives us a bound, or a way to determine what is the order of any given unit, modulo n. Here, n is going to be some composite number. And for our purposes, we want a composite number, but we don't want it to be very composite, because for a given size of n, if we want n to be 2048 bits, the more prime factors means that every prime factor is going to be smaller. So the best case scenario for us is going to be that n is actually just a product of two primes, okay? Two very large primes. So you can actually prove an Euler 2.0 version just for those numbers. So I'm going to propose that you actually try to prove this. No, I didn't mean to grab it. Prove this theorem instead, that if you have n is a product of two primes, p and q, and d is the GCD of p minus 1 and q minus 1, then it turns out that the order of a is a divisor of that number, of p minus 1 times q minus 1 divided by d. by the way, this is if I have this, if this is n, if n is pq, then phi of n is p minus 1, q minus 1. So you see that this is an improvement. This is an improvement over Euler's theorem. Okay, so every unit, every a that is relatively prime to pq has to satisfy this. So every order is smaller than the Euler phi function if there is a GCD, which there is. So for example, here, our primes are going to be very large. 2 is small. So p minus 1 and q minus 1 are even. So at the very least, there is a 2 in here. So if p and q are odd, then you have that at the very least, a to the phi of n divided by 2 is an exponent that works to make it 1. Okay. So anyway, try to prove this this theorem, so you can see why that is true. Now, the discrete logarithm problem is based on trying to solve an exponential equation. What is the power of a that will give me given b? The RSA cryptography is actually based on a polynomial equation. So how do I tell, given an exponent e and a number c, what number raised to the eth power gives me c? It's a different problem. And this problem, if we try to do this problem modulo p, then it is actually a very easy problem to solve. Because if p is prime, and p is going to be my modulus in the equation to be solved, then if you have an exponent that is relatively prime to p minus 1, then there is a solution. And in fact, there is a unique solution. Let me emphasize that. There is a unique solution to this polynomial equation. This polynomial equation is given by c to the dth power. You are essentially doing, as you would try to do over the real numbers, complex numbers, you're trying to take eth roots, right? That's not a thing that is defined in modulo p arithmetic, but there is something that works just like it. If you find the inverse of that exponent, d is the multiplicative inverse modulo p minus 1, then that is the exponent of c to the d works to be a solution of this equation. And this congruence is modulo p minus 1 instead of p, because modulo p, we know, because of Fermat's-Taylor theorem, exponents of numbers work modulo p minus 1. Okay? So again, I would like you to try to prove this if you've never seen this, especially, I mean, that this power works, but also that it is a unique solution, the unique solution that works like this. Why do we want a unique solution? We do want a unique solution because when we are going to do cryptography, we're going to send something like this. I'm going to give you a C that is an eth power, and you have to retrieve x, but if there were many different values of x that gave me a solution to this, then it wouldn't make any sense because there would not be a unique message that makes sense. Well, in fact, maybe if there were just some small finite number of x values that worked, maybe all the other ones but one would actually be a message that it's, you know, in plain English once you decrypt it. So maybe it will work actually, but in principle, we want a unique solution, so we have a one-to-one function of plain texts and cipher texts. All right, so prove that one. But you can see that we can crack this very, very quickly, very efficiently, because if I am working modulo p, then I can just find what is the inverse of E modulo p minus 1. However, if we're working modulo n, and the n now is a product of two primes, pq, then well, this seems to be that I'm stating exactly the same theorem, essentially, that take two primes, two odd primes, distinct odd primes, take an exponent that is relatively prime to the phi. This is the Euler function, so if we set, again, n pq, this number here is phi of n. So take an exponent that is relatively prime to phi of n, then I can again find the multiplicative inverse of E modulo the way exponents work, modulo n, because of Euler's theorem. Take that exponent, which is the multiplicative inverse of E, and then this equation has a unique solution, which is x is z to the d modulo pq. So again, like, what's the difference? This seems to be very easy also, except that to be able to do this, I have to know what is the factorization of p and q of n, that n is equal to pq, because to be able to do this, this is relatively easy. This is some sort of like Euclid's algorithm problem, but you need to know the modulus. And the modulus relies on the fact that I knew n was pq, so this new modulus is p minus 1 times q minus 1. In this case, knowing p, that is, I know what modulus I have to work on for exponents, is p minus 1. Just subtract 1 from the modulus. Done. But in here, to be able to solve this, now I have to be able to factor n. And that's the key ingredient in the algorithm. So for example, if I want to try to solve this equation, x to the 7 is congruent to 2 modulo 15, then I can do it because I know how to factor 15. 15 is 3 times 5, so the Euler phi function is 2 times 4 is 8, so I just need to be able to invert 7 modulo 8. 7 is relatively prime to 8, so there's going to be a unique solution. So what I have to find is the multiplicative number, the multiplicative inverse of 7 modulo 8, which turns out to be 7 itself. So this is not great for cryptography. That it's exactly the same exponent works. And then just take 2 to the 7th, where the 7th is now this 7, and 2 to the 7 is 8 modulo 15. By the way, to do things like this, we also need to be careful, because to solve these problems, we're going to have to take very large powers of numbers modulo n. But those with the fast powering algorithms, those can be done very efficiently and very quickly. So that is not too bad. So for example, to do 2 to the 7, then you can break, I guess I didn't break it all the way here, you can break 7 as 4 plus 2 plus 1, so that you compute 2 to the 7 would be 2 to the 4 times 2 to the 2 times 2 to the 1. And you compute 2, a square, 2, a square again, 2 to the 4. So you have to do 3 squarings to figure out what the number is. So you get 8, which is the solution. And you can check again that that solution works. 8 to the 7 is 2 modulo 15. All right? So how does RSA actually work? So Alice is going to set up a system to receive encrypted messages from Bob. Okay, it can, if they are both going to communicate, then they would both set up one of these. But the way this is set up is for Alice to receive messages. Again, this can be that Alice is sort of like the credit card company, and we're sending information to this credit card company. So choose primes, P and Q. Those have to be secret. Compute n, which is going to be p times q. That's supposed to be a very large number. Now, Alice does know the factorization of n, so she can compute e, a number e that is relatively prime to, this is supposed to say p minus 1 times q minus 1. Now, notice that many times when you have a prime, when you do p minus 1 might have a lot of small prime factors. So you have to be a little bit careful how you choose your key, how you choose your exponent to make sure that it is relatively prime to that number. And Alice publishes n, the modulus, and the exponent. Now Bob is going to choose a plain text, some number m, which is a number modulo n. So you encode, we'll see in a moment how to encode messages from plain text to a number. And then you compute your number to the eth power. which again, using fast powering algorithms that can be quick, and send that to Alice. Okay? And then Alice, in the meantime, if she knows there's going to be a message incoming, then can compute the multiplicative inverse of E modulo P minus 1 times Q minus 1 and decipher the message. What does Eve know of all of this? What is public? This is public. The message, you need to assume that C is public, that Eve could find it. And that's all that Eve knows. So how can we crack this problem? Well, we'll see in a moment what can Eve try to do to solve the problem. So just as an example of RSA, you can encode messages, like I said, I think in the previous lecture, you can encode messages, for example, like this. And that way, the word no is 1415. So your veterinary, your vet is messaging you, are you going to come with your puppy this week? And you text no. Well, your messaging app is going to encrypt that, so we're going to encrypt the word no. We need to pick a number, a modulus that is at least big enough to encode 2-letter words. So for example, 3,127 works, and it is the product of two quote unquote large primes. And now as Alice, Alice can set up your, I guess Alice in this case is the vet, and Alice can factor this and compute phi of n, so that's 52 times 58, and you can see that there's some small primes that divide that number, but I can pick, for example, E to be 11, and that will have a 1-to-1 map between plain text and ciphertexts. So the veterinary publishes 3,127, which is the modulus, and 11. Then Bob is going to say, no, I can't bring my puppy today. So Bob encodes 1415 for now, and then has to encrypt that message, or the app encrypts the message by raising the number to the 11th power. Again, you would do that instead of just doing a lot of powers of 1415. You write 11 as 8 plus 2 plus 1, and then you do 1415, square it, square it, square it, and then put it all together to figure out that that is 589. So we send that back to Alice. I guess we send a 4-digit number, so 0589. And then Alice can pick that up, find the multiplicative inverse of 11 modulo phi of n, which is 52 times 58. And you can do that with an easy computation using Euclid's algorithm and find that the decrypting exponent is 1371. So Alice now takes the message from Bob, so 589, raise it to the power 1371, and get back 1415, and then using the encoding mechanism, figures out that that message is no. Yes? The size of E, no, I don't think it necessarily does. I'm going to tell you in a moment some note about like how to choose E, but if we're trying to do, maybe it does. Maybe if the E is small enough, maybe this is easier. It can be easier if it's a small number to figure out. I mean, for example, if E is 2, then it's very easy to figure out. Well, not it's still, you still need to factor this. You still need to know these modulus. You don't even know these modulus if you haven't been able to factor 3127 at all. I'll have to look that up. I'm not sure if the choice of E being a small number matters. You can see that even for a small number, the D is sort of like, it's not clear what the D would be a priori. So one note is that the encrypting exponent many times it's picked to be a power of 2 plus 1, because as I said, you're going to do a lot of encryption, you're going to do a lot of messages to the eth power, and if that e is 2 to the n plus 1, that is a very easy binary expansion, and then it's easy to do that fast powering algorithm works really easy for that exponent, because you can just take a lot of repeated powers of m until you get to the 2 to the nth power, and then multiply by m, and then you have it. That's m to the e. And now the role of E, so Eve has N and E and the cipher texts, okay? And it's trying to figure out what was the message itself. So there are two ways that Eve could try to break that problem. Eve has to try to find x, that x to the e is c modulo n. And there are two ways of doing this. You can do just modulo n, so like I can factor n myself. I can try to factor n. Again, like the sizes of these two primes that we are using is such that factoring n right now would take, like in the order of years, but this n can be changed very quickly from message to message. So that is a very hard problem. Or find x in some other way. We don't know that there might be other shortcuts to find x in some other ways. Again, like what you said, like, okay, what if e is very small? Is there some way to figure out what the d would be? Is there some shortcut for some particular bad choices of e? This is the kind of thing that cryptography studies. Okay, so let me before I go on to that, so there are two problems here that we also want to address. Is like the first one is how to we are going to need two very large primes, so we need a way to produce at scale very large primes. And second, the other problem that we need to address is, are there algorithms to factor numbers quickly? So what we're going to do those two one at a time. This, I hope you in the screen, he actually looks like Gauss. This is something that I found online, and then I figured out this came from some Reddit post, this image that is allegedly a prime that looks like Gauss. So I was at first like, that they didn't do that. They didn't check that it's a prime. So I went in, and whoever built this, they knew what they were doing. So one, you can figure out numbers. There's some programs that you give an image, and then they'll figure out what combination of numbers will look like an actual image. And then it turns out that there are enough numbers that are primes that you can just tweak, like, in this corner or that corner over here, you can tweak the number enough with digits that wouldn't matter to Gauss to make it a prime number, okay? But first I thought, like, no, they didn't check it was prime. In fact, they did. But they actually did not check it was prime. They checked that it's what we call a pseudoprime, which is a strong pseudoprime is actually the primes, quote unquote, primes that cryptography uses. At the scale, at the size of primes we need, the algorithms, some algorithms can be used to check primality, but it can be very expensive. So there's a way to first, at least, check that a number is a pseudoprime, so it is a prime with high probability, and then you can check whether it is a prime and spend, like a few days running a computer to check that it is actually a prime number. So I'm going to explain both ways of doing this. So first, we're going to build pseudoprimes, and then we're actually going to check that those numbers are primes. So for example, is this number prime? 1, 2, 3, 4, 5, 6, 7, 7, 6, 5, 4, 3, 2, 1. This number is some large number, and I have to check if it is prime. One way to check it is using what we call Fermat's primality test, because we know that if this was a prime, then in fact, every number that is relatively prime to p, if this is prime, well, I know that it is actually odd, so this is relatively prime to this number. So if this was prime, this would have to be 1 modulo p. And that is an easy and inexpensive computation to do, so I can check, is that so? And I did that with magma, and immediately you realize that that is not 1 modulo p, so p is not prime. So that is what we call Fermat's primality test, which is, in fact, a not primality test. We can check things are not primes using this by, well, if we have a prime, then a to the p will be always congruent to a modulo p. So if you find a number a, any number a, that violates this, then it violates Fermat's little theorem if it was a prime, but we know Fermat's little theorem is true, so p would not be prime. So this is not a prime because of, thanks to Fermat. We call such a number a witness, in this case, Fermat witness. It conjures this funny image of like a, a trial where we're checking, and if we're bringing witnesses to the to check if things are primes. So this is a witness to, in this case, is a Fermat witness that this number is composite. By the way, if you're going to remember anything out of my lectures, maybe it should be that this is not prime, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 is prime. So if you ever need a large prime, that's one easy one to remember. Okay. But the problem is that there are numbers that will fake you out on that account. So for example, if you have 341, 341 does satisfy that 2 to the 341 is congruent to 2 modulo 341. But if you try 3 to the 341 is 168. So this one, 3 is now a witness for the compositeness of 341, which is not prime, is 11 times 31. So Fermat's little theorem is an if-then statement. It's not an if and only if statement, so you cannot use it to prove primality. You can use it to prove that something is not prime. But it can be quite effective. Yes? It's 341 Mansfield Road. Yes, that's the address for the mathematics department. So at UConn, that did not occur to me. Yes. Thank you, Keith. Okay, so these are problematic. Some numbers that there are values of A that are not witnesses when some other values are witnesses. Okay, and there are even worse cases. Do you have an address that is 561? Is like MIT at 561 Mass Ave or something? 00561. 43210. Nice. All right. Irrelevant, Your Honor. Okay. 561 has a very weird property. 2 to the 561 is congruent to 2, 3 is congruent to 3, 5 to the 561 is congruent to 5, and 47, and 411. And 561 is not prime. It turns out that for every single integer, this happens. So these numbers that are not prime, you notice that it works even for 11, that is one of the divisors of the number, it still fakes you out. Over there for 3, it fakes you out. So you cannot use Fermat's little theorem to check that this number is in fact composite. Yes?
Do you have to check all of them or just the primes?
I tried prime numbers because, well, if it works for 2, it works for 3, will work for 6, and so on. But it turns out that it works for every single integer. You have, so yeah, A to the 561 is congruent to A modulo 561 for all integers A. Those rare, they are rare, but they do exist, and they have been proved to be infinite. they are called Carmichael numbers, and you have Robert D. Carmichael to blame for. Carmichael apparently did work in number theory and differential equations and special relativity. Did a lot of different things. And apparently in differential equations in particular, I don't know if Keith knows or anyone knows, apparently he did some big contributions. The Wikipedia page says that it's like some of the very first very important contributions by an American to differential equations. I don't know what those are. But in any case, here is Carmichael. You can think of Carmichael like as a very evil person. Because it ruins Fermat's little theorem for us as a primality test, because there are Carmichael numbers. And then, by the way, Carmichael was born in 1879. You would think that Fermat or Euler would have already come up with these kind of numbers. 561 is not even that big, but Carmichael realized that there are numbers that have this very strange property that maybe Fermat or Euler, they didn't even think that there could be a number like this. In any case, the Carmichael numbers were discovered at 561, were discovered by Carmichael. 50 years later, there were proved to be infinitely many Carmichael numbers. So now the other thing we're going to use for a better primality test is that if you have a prime, then it turns out that the equation x squared is congruent to 1 modulo p has exactly two solutions. Does anybody have a clean reason for why this is true? Do you know why? Maybe a higher brow reason why this has to be true? What is it? Oh, ramification. Maybe not so highbrow. Yes. Exactly. If you think of x squared minus 1 equals 0 over the field Fp, then we know that polynomials over fields have at most two solutions. Plus or minus 1 are solutions, so those have to be exactly the only two solutions. But if P was composite, then there are more solutions. There can be more solutions to x squared is congruent to 1 modulo P more than 2. So if you're trying to find that something is not prime, and you figure out that there are more solutions than plus or minus 1, then that number cannot be prime. And well, we're going to use that idea to what's called the Miller-Rabin test. So take a number that is prime and write p minus 1 as 2 to the k times q with q odd. Then take a unit modulo p, then always one of these happens. Well, we know that a to the p minus 1 is 1 by Fermat's little theorem. So what is the order of A? It has to be a divisor of 2k times q. Q is odd, it doesn't have to be prime, but the order either divides q itself or it divides one of these powers of 2 to the k times q. So at some point, we're going to get 1. Maybe the order was p minus 1, and that's the very first time you get a 1 as a power of A. But if that is the case, if I divide that exponent by 2, those have to be solutions of the equation x squared is congruent to 1 modulo p, right? Because of this reason, if this is the very first time this happens, this is the order of A modulo 1, or the order, the first number of this type that the order divides this number, then if you divide this by 2, then you have to have a minus 1. If this were the very first time you got a 1, this has to be plus or minus 1, so it has to be minus 1. So primes have this property, but not primes very often fail to have this property. Okay? So we use that in our favor to reverse it, and in the contrapositive to prove things are not prime. Okay? So for example, let me just show you how this works for a prime. A prime p minus 1 is 12. So 2 to the square times 3. Let a be 2. Then 2 to the 3 is 8. That is not 1 modulo 3. Okay. But 2 to the 3 is 8. That is not minus 1. 2 to the 6, though, is minus 1 modulo 13. So it satisfies the conclusion of that proposition. So we actually say that if we have a number that is to be tested for primality, that is going to be a composite number, and we factor it like we were factoring primes, and then take A to be a number that is relatively prime to n. By the way, how you might wonder, like, well, how am I going to know that if already that might be too expensive? Well, if we somehow find a GCD, then we have already factored n. So we win either way. So usually you try A, you try this, it is 1 because n is p times q. So if I try A equals 2, then usually it doesn't work, and then you know that you have something that is relatively prime to n. Then that A will be a Miller-Rabin witness for the compositeness of n if it violates the conclusion before. Either A to the q is not 1 modulo n. I'm sorry, it has to satisfy all of these properties. So it has to satisfy that this is not 1 modulo n, and none of those is minus 1 modulo n. Okay? So if that happens, then we know that there's got to be some time that there would be a, anyway, one of those is going to be sort of like at a root of x squared equals 1 that is not plus or minus 1. All right, so for example, take 33. 33 and minus 1 is 32, 2 to the 5 times 1, and then we check. 2 to the 1, because 1 is q here, 2 to the 1 is not 1, modulo 33, and then just compute 2, and then 2 to the 2 times q, 2 to the 4 times q, and so on, and then we can see that, oh, by the way, these are powers of 2, is not every even number, are powers of 2 times q, so I just have to do 2 squared, and then 2 to the 4, 2, 4, 16, those are not minus 1 modulo 33, so A equals 2 is a Miller-Rabin witness for the compositeness of 33. Okay? All right. So what happens with 561? 561 survived the Fermat primality test. I can't say that it's prime yet, but if I try the Miller-Rabin test, then what happens? N minus 1 is 560. 560 is 2 to the 4 times 35. That's my q now. Try A to the 35. Take A is 2 to the 35 is not plus or minus 1. And then try 35 times 2 times 4 and times 8. And then I get 166, 67, and 1. And none of those are minus 1s. Okay, so A is equal to 2. It's a Miller-Rabin witness for the compositeness of 561, so it did not survive, and it is not prime. Yes? So if this was a prime, then this result tells me that either A to the q is 1, or one of these values is minus 1. If it is prime, it has to have that property, because it has to be that I'm either finding that the order of A was q or a divisor of q, or it is not, and then the order of A divides one of these powers, and the previous power, so divide that power by 2, that previous power has to be a minus 1. So there is a number in this list that is a minus 1. Okay? So when I look at this list, I don't find that A to the q is 1, so the order does not divide q, and I don't find any of these to be minus 1. So what that means is that, in fact, I have found what I said. I have found something peculiar, because this number is 1, and this number would be a square root of 1 that is not plus or minus 1. So what this means, by the fact that this is now square it, I get this, I get 1, 67 is a number whose square is 1, but 67 is not plus or minus 1, so this cannot be a prime number, or it would violate, this Lagrange's theorem on roots and polynomials. Yeah.
And then, so for that last one, when you had a to the power of a times 35 is converted to 1,
Yeah.
why is that not satisfied? Because you just need one of those to be converted.
It has to be congruent to minus 1. One of them has to be a minus 1. Okay. I know. Well, I don't know. I mean, if 2 to the n minus 1 was not 1, then I know this is not prime by Fermat's little theorem, right? So I'm assuming that I have already checked Fermat, and that is a 1. Okay. But I don't even have to check that, because if none of these are minus 1, then to the n minus 1 is also not going to be. Well, if none of these were 1s, in any case, one of these has to be a minus 1. And since none of them are minus 1s, and this one is not 1, then I'm done. And it's this one is not plus or minus 1, then this cannot be a prime number. Yes?
So would like the hardest primes to check with this then be like any prime is like 2 to the k plus 1, just like very large k?
What primes are those? Those are Fermat primes. Those would be Fermat primes, which are notoriously also like, I mean, there are other methods to check for primality, for Fermat numbers, or to try to factor Fermat numbers. But Keith, do you have a comment on?
We don't think there are more than like 5 or 6 Fermat primes.
Well, we don't know that either, right? Yeah. Okay. So why is this useful? So here's another example. Is the Miller-Rabin test always good? It turns out that there is also numbers that do have Miller-Rabin inconclusive numbers, so things that are not witnesses. For example, this number is composite, 2047, but when you try the Miller-Rabin test, this number is 1 right here, and that's all you needed to test, and that's it. That's it. You have that the Miller-Rabin test is inconclusive, and then what we say is that 2047 is a too strong pseudoprime because it passes the Miller-Rabin test for 2. But however, if I try 3, then it turns out that it does not work for 3. So 3 is a Miller-Rabin witness. So it is not a 3 strong pseudoprime. Now we can do this with like 20 different bases and see and get more confidence. But like, what kind of a confidence do you get with this? Well, it turns out that if n is a composite number, then these strong pseudoprimes are rare, in that at least 75% of all the numbers from 1 to n minus 1 are witnesses, at least 75%. So we, unlike the Carmichael numbers, where there are numbers that, every base is not a witness, for Miller-Rabin tests, there are at least 75% of all the numbers are witnesses. And that gives me a way to check what is the probability of a number being prime. Because if I try k different witnesses, and none of them are witnesses, then the probability that n is prime, now it becomes 1 minus a fourth to the k. Okay? So if I've tried 20 witnesses, then I have and none of them are with actual Miller-Rabin witnesses, then I'm very confident that this number is prime. I haven't proved it, but I'm very confident that it is a prime number. So for example, with this number, let's try if this is prime. I tried to do my Miller-Rabin test, and it turns out that with 3, I get that 3 to the q is minus 1 modulo n, so that is not a witness. What does that tell me? It tells me that now this number, the probability that this is composite, is less than 25%. Okay? And you keep trying, And it turns out that 17, if you, for whatever reason, you went from 3, try 17, 17 is also not a witness, but 23 is a witness. So by 23, I get that 23 is a witness for its compositeness, so it is a composite number. And it is one of these that it is a strong pseudoprime for several bases. By the time when I've tried 2 of them, then I thought it was a composite with that the probability that this was composite was less than 6.25%. So I was starting to feel sure, but then with the third one, and we see that it is actually composite. So it's just giving you an estimate of what is the probability that a number is prime. So how do we find large primes? And in fact, are there any? Well, we know there are infinitely many primes. And the prime number theorem tells me how many primes to expect. So when they were trying to build that number that looked like Gauss, if the number, I think the number was something like 10 to the 4,000 or something. I think the image was like, yeah, like a 4,000 numbers, okay? So what is the probability that that number is prime? You throwing in here, the prime number theorem tells me 2 things. You can interpret that as a probability statement. The probability that x is prime is about 1 over log of x. So if the number is about 10 to the 4,000, that tells me that the probability that a number of that in that range is a prime is about 1 in 4,000. So if I actually reserve the last 4 digits of my number, the ones that were in the corner of that image, and move through, say, 5,000 of them, I expect to find at least 1 prime among all of those. So, and it also tells me what is the expected number of primes in a given interval. So a dyadic interval, for example, I can get an estimate. This number, it goes to 0, but this goes faster. So this goes to infinity as n goes to infinity. So there are a lot of primes in those intervals. So if I want a prime that is of the size 2 to the 2048, I know there are going to be some primes of that size between 2 to the 2048 and 2 to the 2049, that there is a whole bunch of primes in there, okay, using the prime number theorem. So for example, let's do this. Let's find a prime that is approximately 10 to the 20. How do I do it? The probability that a number of that size is prime is about 1 in 46. Okay, so all I have to do is take 10 to the 20 and add k. You probably don't want to add an even number, but let's just say add k. And then there should be, with k between 0 and 50, the prime number theorem tells me that there should be a prime in there. So that's what I did. And I'm not going to be checking every single number. I'm not going to run a primality test because that's going to take time. I'm just going to first find the strong pseudoprimes. So for each one of those, actually I did up to 46, try 20 Miller-Rabin witnesses and see what happens. And it turns out that only 1k worked. 10 to the 20 plus 39 is prime with probability 0.99999999999 and so on. So this is very likely a prime number. Okay, and this is the only one in that little range from 1 to 46. And so that one looked like prime, and then you can actually run a primality test on this one, and it turns out that it is prime. Okay, so that's how I found a large prime in the interval that I wanted. It's relatively cheap to do the Miller-Rabin test because it's just doing a bunch of congruences, and with the fast powering algorithm, I can check these congruences very quickly. So it tells me where to look before I actually go to do the expensive computation of, is this actually prime? I do Miller-Rabin. Yes?
So earlier when you had the Miller-Rabin example and you found that it wasn't prime, I think earlier you had one where it said it was inconclusive. So when is it inconclusive? Is it when one of those is negative one?
When I find a number that is not a witness. So if it is, if I find a witness, it's a witness for compositeness, then I know it's composite. If I find a number that is not a witness, then I don't know yet. But because of the probability of randomly choosing a base and picking something that is not a witness, that was 1 in 4 that I would have picked that it was composite and that number was not a witness, was 1 in 4. So maybe I got unlucky and I picked a number that it was not a witness. So I try again. And if that is not a witness again, now the probability of that was 1/4 times 1/4. So now it's unlikely that I picked 2 numbers at random and they were not the witnesses. So I keep going like that, and then that's giving me more and more confidence that this number might be prime. You have to keep going with the Miller-Rabin test. You keep going until you are satisfied that the probability is tiny that this number is composite. But it's not a proof. However, there are proofs. I think I'm just going to tell you a couple things. One is that if the generalized Riemann hypothesis holds, then every composite number does have a Miller-Rabin witness below a certain bound. Okay, so potentially, if you had tried, first of all, you believe the Riemann hypothesis is true, and then if you have tried every single number to be a witness up to this bound, then yes, up to the Riemann hypothesis, this number is prime. So you could actually use the Miller-Rabin to prove primality, but I'm guessing that if this is true, there must be another bound that is Riemann hypothesis free, which would be an even worse bound, but you could do one of these bounds to check. Now, there is also primality tests. So there is a test that actually tests for primality. This was something that made a big splash. The AKS primality test tells you that there is an algorithm that, given a number n, gives you checks that proves that it's prime with about ln of n to the 6th power. So the fact that this was sub-exponential, this was a big surprise that this all of a sudden they found an algorithm of this sort. But anyway, this primality test is pretty much useless in practice, but is good of theoretical value. But then there are other tests that you can use for primality proving, which are actually based on elliptic curves. So I think this is better suited to be in the last lecture. So I'll talk about this next time. So I think I'll stop there for today.